continue our conversation. All right. So what I've done here is I've got some data that I've plotted. Right? And I see that one of these is a good line. So if I look at my R squared value, that measures the deviation between the data points and this trend line that we put in here. Okay. So R squared of 0.86 is not great. R squared of 0.96 is better, but an R squared of 1 is awesome. So I know that it's second order based on that. And I also know that the slope, the 46.452, is my K. So that's my rate constant. Sorry, words failing me. So I know that this is second order. We have plotted all of that data. Okay. And that's our best fit. Go awesome. That was fun. So plots should be easy because you don't have time to plot one of these. But I can show you these and go, which one is this? And you should be able to tell. Okay. So questions about that. Welcome to our friend. So now we're going to talk about the Arrhenius equation. So the rate constant is temperature dependent. Okay. The relationship is given by K, that little k, which is the rate constant, is equal to A times E to the negative EA over RT power. That's a lot of stuff. EA is the activation energy. We talked about that previously. Where's the gas constant? In this case, we're going to be using 8.34 joules per Kelvin mole as opposed to the 0.06821 liters atmospheres per mole Kelvin. T is our absolute temperature in Kelvin. A represents a frequency factor, and it has to do with how often their collisions result in products. It's different for each compound, but that's okay. That's what it is. It's just a frequency factor. And the rate constant decreases with increasing activation energy and increases with increasing temperature. Okay? And this is useful to us because knowing how much energy is required to perform a reaction is helpful because we have the activation energy is very large. You may want to seek out another mechanism by which you can do this because it's going to be difficult to do without giving a lot of energy, and that's going to be consuming. Another form of this equation, ln of k is equal to the ln of A minus EA over RT. That's another form. This equation is a good one to use because it's in the y equals mx plus b format. So a plot of the natural log of k versus 1 over t gives a straight line with a slope of negative EA over R, and the intercept with the y-axis is that frequency factor. So that's one way that we can get to some of these pieces of information. And here's an example of that. So I have some raw data. We took the rate at each of these temperatures. We processed that so that we have 1 over the temperature. And then natural log of K, we plot that, and that gives us this reaction, this line here, y equals negative 9253x plus 24.504. Okay. A is that 24.504. Our slope is equal to negative EA over RT. So our EA is equal to negative 8.314 joules per mole times joules per mole Kelvin times the negative 253 Kelvin, which is this slope number out here, right? So we've rearranged this to solve for EA. So we have our EA, move that to the, so, sorry, we take our R and our T, move that over there, and then we have the negative value on the other side. So we take the R with the R. So that's why we get this slope here. And of course, if we do that, then that gives us our EA is 77,000. Okay, awesome. So we need to make sure that we are able to do that. So we can solve for EA using this. Okay. Questions, comments, problems on that. Now, would you be expected to graph this? No, of course not. Might you get a graph like this and be asked, what's the EA? Sure, maybe. Might you be asked what the frequency factor is? Yeah, maybe. I might show you, or I might put up the Arrhenius equation and say which of these graphs represents how we plot that. Okay, you need to have to write out identify the one that's the natural k versus 1 over t. So that's what we're talking about there. Questions about that? Hopefully not, but let's talk about some potential questions I could ask you based on what we just looked at. So define the terms in the equation. K equals a to e to the negative ea over rt. K is, again, that rate constant. A is the frequency factor. Ea is the activation energy. R is the gas constant. And T is our temperature in Kelvin. Next question. If Ea of one reaction is half the value of another reaction, for instance, 12 versus 24, would you expect the reaction with the higher value or lower value to predict more product at the same temperature? Why? Well, I would expect at the same temperature that the one that has the lower EA will be the one that produces more product. Okay? So the one that here is 12. I would expect that. And again, that's a lower barrier that it has to get over to be able to get to product. Which curve below would you expect to have the greatest rate and why? So we have two things that are plotted here. We're looking at e to the negative ea over rt versus ea. You can see that the 100 is here and the 0 is there. We can also see this in terms of temperature. So we can see that our ea in this one is 20 kilojoules and this one is 50 kilojoules. Which would I expect to have the greatest rate? Well, I would expect the one that's represented by the ea of 50 kilojoules. That should have. Okay? Questions on that? I hope not. But if you do have questions, let me know. Again, standard methods of getting a hold of me: email, phone, drop into my WebEx office hours. Come and see me on campus if you want. Not a big deal. So that takes us through the end of that topic. So I'm going to go ahead and stop, pause here, and we'll be back in a couple minutes. Thanks, guys.